Hello guys, welcome to first law of thermodynamics. We'll be doing the adiabatic process plus equation of it. Now adiabatic process is the process in which we supply no heat, so dq equals to 0, but the pressure, volume and temperature of the system changes even though there is no heat supplied. So for this process to occur, there are two conditions. First of all, the system, the outer of the system should be insulated. The system should be insulated, and the process should happen rapidly, so very fast. So, and also I forgot to mention, for the isothermal part, it is the opposite. So for isothermal, it should be well conducting, and also the system. So the process should take very slowly for isothermal. And now, if dq equals to 0, then from first of thermodynamics, we have dq equals to du plus dw. So du plus dw will equals to 0. That means du equals to minus dw. That means if this, well, yes, these are the negatives of each other. You can also write this, and you can also write that. So now for the adiabatic equation. Now this is very important, and this is also lengthy, and there are several steps that you need to follow. First of all, what you will need is will need du in terms of Cv, like we did for the relation between Cp and Cv. Now first, the system, let's say we have a system at PVT with 1 mole, we're taking 1 mole. Now first of all, at constant volume, we apply some heat dq, and then the volume remains fixed, and there is some change in temperature dt. So now we have dq equals to du, and we have, well, since dw equals to 0, as dv equals to 0, and here dq equals to ms dt, and m is 1, so cv dt. So from here we get du equals to cv dt. Now what we'll do is, now we'll take the original system and we'll have it in an adiabatic process. Now here there is no heat supplied. So dq equals to 0. And here even then, some volume, there is some change in volume, increase in volume, with let's say same change in temperature dt, and also, well, change in pressure, we don't write dp. So now for adiabatic part, we have, well, du plus dw equals to 0, right, as we discussed earlier. So here du is cv dt, and the work done, well, is just pdv equals to 0. Now, like in cp and cv part, we need dt in terms of, well, some other things. So now we use ideal gas equation, and we get pv equals to nRT. N is 1, so RT. Now we differentiate both sides with respect to dt. Now here, unlike in the Cp and Cv part, here pressure and volume are both variables, so we need to use the product rule for derivatives, which is P dV by dt plus V dP by dt is equals to, well, R is constant, it goes outside, dt by dt is 1. So here we get P dV plus V dP equals to R dt. Now we can just write the dt as in itself, so this is R, so we can put this 2 in 1, so it becomes, well, Cv pdv plus vdp by R plus pdv equals to 0, right? So we'll just open this CVPdV plus CVVdP plus, well, I'll take the R common, which is PRdV whole divided by R, and we can multiply both sides with R. Well, it becomes 0. So now we have R right here, and let's use what we learned in the previous video, that using R equals to Cp minus Cv. So here this becomes CVPdV plus CVVdP plus PCPdV minus PCVdV equals to 0. Now here PCVdV and we have PCVdV, they cancel each other, so we get PCV dPCVV plus PdVCP equals to 0. Now what we now do is an important step. We divide by PVCV. So now if we do this, here the CVV cancels, giving us dP by P, plus here let's just take Cp by Cv right there. This is known as the ratio of specific heat constants, where this is gamma. I'll write in the next step. And now we get dV by V, because pressure cancels, giving us 0. Now, as I said earlier, this is gamma, dV by V equals to 0. Now what we do is we integrate both sides. So this becomes integration of dP by P plus, well, the constant goes outside the integration, giving dV by V equals to integration of 0. Now the integration of, well, derivative by its function is the log natural of the function plus, well, gamma log natural of V equals to, well, integration of 0 is a constant, so we can choose our constant. Let's say it is ln k, such that we have ln everywhere and it will be nicer in the end. Now using log property, this gamma becomes a power of V, become ln p plus ln v to the power of gamma equals to ln k. Using another log property, we have ln p v gamma equals to ln k. Now these ln and ln cancels, giving us p v gamma equals to constant. So this is the required adiabatic equation. Now also this is p1 v1 gamma equals to p2 v2 gamma, right? Now from PV equals to RT, we have pressure equals to RT by V, which we can use in this equation. Let's just say this is the main equation, which was equation 3. So 3 becomes RT by V into V gamma equals to K, or TV gamma minus 1 equals to K by R, right? Therefore TV gamma minus 1 equals to another constant, because these two are constants, and, well, ratio of constants is just a constant. So again we have T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. Again from there we can also have volume equals to RT by P. So then again in 3 this becomes P RT by P gamma equals to K. So this is pressure to the power of 1 and this is minus gamma. So P1 minus gamma into R gamma T gamma equals to K. Well, pressure 1 minus gamma T gamma equals to, well, let's just do it directly. R gamma is constant, K is constant, we put that there. This is just another constant, right? So here P1 minus gamma T1 gamma is equals to P2 1 minus gamma T2 gamma. This is it for the adiabatic equation. If you learned something new, please like and subscribe. Thank you.